All right, everyone, we're going to get started looking at just some examples, really, of dealing with some of these line integrals. And so, in the bulk of it, I'll probably just worry about the setup and kind of introduction of that arrangement, and maybe leave the final calculations, evaluating those integrals to you. I can write up I can put in the final answer, but some like the U subs and the formal work, maybe I'll leave that off. But really, the context of the examples is that setup, kind of seeing how those components are coming together, looking at the path, the curve, the line that we're integrating across through with these functions. Okay. All right. So let me start to share the docam, and we'll get going. All right. So here's some of our examples. I'll take it from the book, right? Our calculus 8th edition from Stewart. Okay. And let's look at some of these numbers. So remember what we're doing, we're integrating across some path C, some function f of x or f of x y, f x y z, d s, right? So we're kind of imagining in 2 space, right, in R2, or even in R3. We'll try to look at an example as well, hopefully. We're going to have some path, some line, some segment of a curve that we're most likely going to be able to present right as a vector function, right, which is, again, this kind of x of t, y of t, depending on our parameter, whatever letter we may choose, t, u, s, v, whatever it might be, okay? We can identify our different locations on that curve. And this idea that we have this little arc length segment ds that we're letting this function act upon, right? We're going to use it as our base, and we have our heights with the function, okay? The description we had yesterday. And that ds component, the little arc length, dx dt squared plus dy dt squared square root dt, okay? And so what we'll see also in examples that we'll have some integrals that maybe we're not dealing with just ds, maybe we just want to see a dx integral, a dy integral. It's still some path in space, but maybe we're only worried about how does that function kind of acting in that dx segmented progression, okay, integrating with respect to x only. And so we're going to see how that x of t component comes in to get an integrating factor, okay? But we'll get into that in an example. But there's our discussion. We'll do a vector field hopefully as well. And let's get going here, okay? And so as I mentioned, the big part is creating, as identifying what that parameterization will be for our curve, our path. In an initial couple of examples, they give it to us. Other examples, we're gonna have to do it on our own, okay? So let's just kind of start to jump in, and let's check out here, okay? Let's just start for ease. Problem number 4. This is on page 1124 of the text. Evaluate this line integral, and we have this integral across C. Our function here, x times e to the y ds, and then C is this line segment from 2, 0 to 5, 4. All right, so really, let's first think about that path C. And I'm not going to be terribly precise. I'm going to do my best, of course, but in terms of just trying to get this graphed, I might move a little quickly. All right, so here's our coordinate system. We're starting, and again, this is kind of where we need to pay attention here. Here's my initial point. This is where we're starting, and this is my final, my terminal point. Because as we start to go through, we want to keep track of how we're going through, how we're tracking along that curve. Okay, because whether we're going right, working our way to the right, to the left, right? When we start to see those circles, are we going counterclockwise? Are we going clockwise? Right? The direction that we're traveling, traversing, that path is going to play a role in what we get for that final calculated result. Okay, because if we're working backwards, or we're going to get a negative if we're walking that path, that curve C backwards as compared to, we want to start here and here. The final integrator is going to be the opposite sign because we're going the opposite direction. So we have to think about the orientation, how we're traversing that path. All right, so let's start to work on those. For our path is starting at that point, x is 2, y is 0. There's my initial point. And we're stopping at 5, 4. As best I can line that up. There's my final or my terminal point. So our segment C, and I'm going to put these little arrows to identify that we're moving in this direction. We're starting here and moving in that direction. And so as we start to see that vector valued function, we want to make sure as we start our progression of those time steps t, that when I start, and again, that t can be anything. We can start at 0, we can start at 1, we can start at 2, right? That we're following this path and kind of progressing. Okay, when t equals 1, when t equals 2, 3, so on, whatever it might be, we're working in that direction. Okay? And so in the textbook, in the discussion, they have some means of identifying these components. And if we think back to our discussion, our equations for lines, back in, I think it was section 12.5, if I'm correct. It's in the first chapter we had discussed. Okay. Remember that we had talked about that R of t was equal to, right, that R sub 0, our initial point, plus t, that parameter, times our direction vector. Okay. And if we start to think about that v was our direction vector, x2 minus x1, y2 minus y1, right? And so if I start to put some of these details together, R sub 0, which was x1, y1, my initial point, or I can probably more effectively call it x sub 0, y sub 0, right? Plus t times x2 minus x1, y2 minus y1. Start to doing that vector work. X sub 1. Let me bring in that parameter t. X sub 2t minus y, x sub 1t. And again, I know it's a little bit jumbled here. My apologies. Adding here, x sub 1 plus x sub 2t minus x sub 1t, y sub 1 plus y sub 2t minus y sub 1t. A little bit of rearranging. I know it's a long, drawn out process to get to this result, but just kind of seeing how this comes about. What we can start to see though, we can get this kind of x sub 1 times 1 minus t plus x sub 2t, y sub 1 times 1 minus t plus y sub 2t. And if I start to break those components up again, 1 minus t times r naught, my initial point, plus t times my final point we'll call r sub 2, but again, I know it's going to be r sub 1, but that final point, okay? And so as we start to work on that, we can start to incorporate that in terms of our particular function. So in rt then, we can do 1 minus t r0, my initial point here, 2, 0, plus t times my final point, 5, 4. Okay, and so as we look at that, putting those components together, we're going to get here 2 minus 2t plus 5t, right? Just showing that 1 minus tn, 2 minus 2t plus the 5t. Then for the y, 0 plus 4t. So then our r of t, 2 plus 3t, 0 plus 4t are just 4t. And these creations are going to work for t between 0 and 1. And so this gives me my x of t, y of t for that segment when t is 0, 2 plus 0, 4 times 0, 2, 0, my initial point. As we work our way through, once I get to t equals 1, 2 plus 3 times 1, 2 plus 3 is 5, 4 times 1, 4. We're at that final point, 5, 4. Again, a kind of roundabout work. There's other ways of doing it. We can make an equation for that line. There's other steps we can take, even going back to that 12.5, how we built those equations for our parametric equations for lines there, the same idea, okay? I know a long way around this, but getting towards this path of this integral, okay? All right, so that's the first part, just kind of thinking about how we might parameterize, how we might deal with that line, that curve, to integrate across. And so let's jump back to it. We just finished. C is this RT, 2 plus 3t, 4t. Okay, copying that down, sorry. So this is my x and y. ds, that's square root, dx dt squared plus dy dt squared dt. So again, if x is going to be 2 plus 3t, dx dt, taking a derivative, right, just kind of like our u subs, 3, right, y 4t, dy dt 4. So in this case, just constants. Other problems we'll get, they'll be variables, variable expressions. So that way, my ds is going to become this factor, dx dt is 3, dy dt 4, 3 squared 9, 4 squared 16. Adding those up, we get ds square root 25, which is just 5 dt. So there's a substitution for my ds component. Okay, and let's not forget with this part that parameterization, that's going to go from t between 0 to 1. So that's giving my limits of integration. So when I start to rewrite them, this becomes this integral from 0 to 1, x, which was 2 plus 3t, e to the y was 4t, ds, jumped the gun, jumped ahead of myself, ds 5 dt. Okay, so these are the, there's my x, e to the y, ds became 5 dt. T is going to go from 0 to 1, the way we parameterized. That constant 5 built in from that arc length, that ds component. Okay, and so as we start to set up this integral, the 5 can go outside, integrate from 0 to 1, 2 plus 3t, e to the 4t dt. And in this case, distributing e to the 4t in. All right, we're integrating those components. So as we start to work this through, right, even if we wish, we can separate, bring out that 2, okay, 10, 0 to 1, e to the 4t dt, bring out the 3, 15, integral 0 to 1, t e to the 4t dt, right, separating that sum into their own individual integrals. As we start to evaluate this piece here, a u sub, right, just because we have the power in that exponential other than just t alone. So just to make sure I keep track. This case, the t times e to the 4t, there's a by parts integral. Okay, evaluating, so on. So that's what I mentioned. The setup we'll work on. The big part is that parameterization of c, how we rewrite that integral in terms of our parameter t, and then working through. And I can put up that solution in the notes, what that should hopefully work out to become. Okay, so starting from that image, what we're integrating, what path we're integrating across, how we can parameterize that path, that curve, this segment from 2, 0 to 5, 4. Again, some build up here, the work in 12.5 on writing equations for lines, a big help, I would say, really, and going from that stage, okay? But depending on what we use for our parameter, it might go from 0 to 1. We can even write that equation for this line segment, you know, as that slope-intercept form, y equals mx plus b. We can put in that form, and right, if we use x as a parameter, let x equal t, then we're going to go from t equals 2 to 5, and we can just use that way as well. I'll let you think about that. If you have questions about that, let me know. But it's an option, okay? And then once we get that parameterization done, we're here, setting up, getting those components to substitute in to get everything in terms of that parameter t, or whatever parameter we want to use, w, s, q, okay, whatever we like. And then evaluate. Okay, so that was number 4 from the book. As I mentioned, there might be some cases where maybe we're only integrating with respect to one particular variable. So in this case, let's check out the next even problem, number 6, okay? Example number 6, still the same page, page 1124. Integrating over this path c, e to the x dx. So in this case, we're only integrating with respect to x, okay? But then C is the arc of the curve. X equals y cubed from the point, oh, x, yeah, y cubed, there we go, from -1, to +1, +1. I guess I should have, sorry about that. Angled is better, but that's all right. All right. So our arc x equals y cubed. So when x is -1, y equals -1, right? So this, again, my initial point. This is where we're starting. Going through, we're going to end at 1, 1. Let me borrow that, and I can put my label down here. There's my terminal, my final point. Okay. So as we start to go through, this is going to look something like so. Again, maybe not perfect, but we're starting and working along that pathway. All right, so there's our arc C, right? So C, that x equals y cubed. So in this respect, it's kind of already parameterized. Our R of y, we could say, x is going to be y cubed, y is y. Right? That's one way to deal with it. Okay. Or we can say, let's let x, or let's start off with y. Let's y be equal to t, since y is not changing. So then x is going to be y cubed or t cubed. So then r of t can be given by t cubed, comma, t. Right? We have variations, or we can use different letters. Right? So whether you want to use y as your parameter, t, which are more common seen, anything else you may choose. It's just a symbol that we're letting our functions depend upon. Okay? And so now we do so in this case, right? We saw here in that function that the y is going to go between, sorry, not 1, from -1 to 1, right? Looking at those pieces, these are my limits of integration. Or if we switch it into t is going to go between -1 to 1, right? Because y is just following that parameter t, so we can do it that way as well. All right. And so then when we start to see this integral, here, we're only integrating with respect to x. But remember, from our r, x is equal to either t cubed, or we can even do it in terms of y, up to you. So then when I look at that derivative with respect to t, with respect to that parameter, dx dt, 3t squared, or dx is equal to 3t squared dt. So this is giving us our means of replacing that dx integrating factor in terms of our parameter t. If we had kept it in y, we'd have a parameter in terms of y, integrating factor in terms of y. Okay? So this becomes this integral from -1 to 1, e to the x, but the x was t cubed. Dx became 3t squared dt, right? And in this case, this is something kind of nice because that's just a u sub for our integration, okay? But setting up those components, the big part. So even if we don't have that ds, right? That ds is that more arc length, so we need that square root component. But this is just dx. Dx, if we have it parameterized, x is t cubed, dx dt. Move that dt to the other side, we get this integrating factor, just like a u sub really in that creation, okay? And again, I'm going to leave the actual final integrations for you to work on. The setup is the critical part, okay? All right, so with that in mind, that part, boom. Let's do one other problem 2D, and then we can start to look at also a vector field problem in 3 dimensions to kind of get that incorporated. So this next example, let's check out problem number 8, okay? All right, so number 8, still same page, just working our way through because these are some decent examples for those different characteristics that we're looking at. This integral of x squared dx plus, all right, so now we're incorporating these two kind of separate integrals into this singular line integral, okay? And then C consists, watch following the wording of the textbook, consists of the arc of the circle, x squared plus y squared equals 4 from the point 2, 0 to the point 0, 2, followed by, right, because now we have these two different segments, portions, piecewise defined curve, if you will, to follow, followed by the line segment, from 0, 2, 2, 4, 3. All right. Okay, here we go. So we're starting off with this arc of a circle, x squared plus y squared 4, right? Circle, center at the origin, 0, 0, radius 2, going from 2, 0. There's my starting point, up to 0, x is 0, y is 2. So this part of our arc of our circle, boom. And then after that, going to this segment, and this should be hopefully connected, this pathway, not broken up. I can have a jump discontinuity, if you will, going from 0, 2, over to 4, 3. Okay. So we're integrating over this total path C. But hopefully we can see, we can separate C into these kind of two distinct parts. Distinct parts. We have this part, C sub 1, that arc of our circle, and then the line segment are C sub 2, right? So C is going to be the sum of these two paths put together. So then, as long as we can parameterize those two, we keep the same information in our integrals because it's still the same function, the same action operating along that path. But now we just have to kind of separate, parameterize accordingly those two paths. Okay. And so let's start to work on the C sub 1, right? That circle with radius 2, our typical means of parameterizing circles are cosine theta or R cosine t, R sine theta or R sine t, right? We can use theta as our parameter if you want, or t, since most often we're looking at t. So then this radius is equal to 2, right? So in this case, for our R of t or R of theta, I can put that below as well. We're going to get, for the x part of it, 2 cosine t, the y 2 sine of t. And what are we doing for t? T is going to start at, right, when theta, when our angle t is 0, cosine is 1, sine is 0, right? So we're going to go from 0. And then where are we stopping? Think about your theta, think about your angles here. X-axis is 0, y is pi over 2. And we could have left that as theta as well. Okay, perfectly fine. And so when we start to pick up our dx, derivative 2 cosine t, derivative that with respect to t, we'll pick up those components for the dx, similar for the y. Okay. C2, we have that work for our line segment before. We had talked about, we can build that up. Okay. Or again, I might think about, okay, in terms of our x direction, how are we moving, how are we starting off? Okay. For that x, it starts at 0, ends at 4, y starts at 2, ends at 3, right? So in this case, starting at 4, or 0, ending at 4, we're going to go over 4 units. We're going to go up, 1 unit. You get from 2 to 3 up 1 unit. So I'm going to kind of jump to it. Let me see if this makes sense for you. We're going to go starting at 0, 0 plus 4t, starting at 2, going up 1 t for t between 0 to 1. Just kind of using those direction numbers, if you will. To get those components. So when t equals 0, we're at 0. When t equals 1, we're up at 4. T equals 0, we're at 2. T equals 1, we're at 3. Okay? So using those kind of direction numbers, again, that 12.5 discussion, we can work on that information. And again, here's our x of t, y of t for that integral. Okay. And so as we go through it, taking that information, x equals 2 cosine t. This means dx is going to be derivative cosine negative sine 2 sticks around t dt. Y 2 sine t dy 2 cosine t dt. So that integral across C1 of that x squared dx plus y squared dy, that component of it becomes this integral from, and you get t went from 0 to pi over 2, x squared, x was 2 cosine t squared, dx negative 2 sine t dt plus y squared 2 sine t squared, sorry, I kept it in blue there, times dy 2 cosine t dt. Dropping some of these parentheses, combining where we can, right? This is going to be 4 cosine squared t times that negative 2 sine t dt, right? Negative 8 cosine squared t sine t dt plus 4 sine squared t times 2 cosine t dt, 8 sine squared t cosine t dt, or depending, we can factor out a negative 8 or positive 8 for that matter. Integrate from 0 to pi over 2. Cosine squared t sine t minus sine squared t cosine t, and then that dt factor out. So it looks like a single integral, like we're kind of more familiar, more used to dealing with. And then each of these integrals, we could use sub and work through. But that's just C1. We'd have to do the same thing along C2. Okay, and so when we're doing C2, that integral, remember, we went from 0 to 1 for t. We had this expression. I'm going to copy that down just a second. We can call r sub 2 if you wish even. That was 4t, 2 plus t, right? So our x was 4t, dx is going to be 4 dt, y is 2 plus t, dy is going to be 1 dt, and our t ranged between 0 to 1. So let's start to put these components in. X 4t, dx 4 dt, y 2 plus t squared, dy dt. And so similar to what we saw above here, I'm going to jump a little bit faster. If we have these polynomials, we're going to get here 4t squared, 4t times 14, 16t squared times a 4. 16 times 4 sounds like 64 t squared dt plus that binomial squared, 4 plus 4t plus t squared dt. Rearranging, combining like terms, 65t squared plus 4t plus 4 dt. We can factor out, or we can't factor out with that 65, pardon me. But here we are, power rule. And so the final solution is going to be the sum of those two integrals the way we've just parameterized. And again, I can fill in that answer to finish up, but there's that work. Interesting stuff here, I'm hoping. Okay, let's do one more, and let's try to bring in a vector field problem. Right? I introduced it, but let's kind of see it more so in action with that formula. So this next example, let's check out, jump ahead, way ahead, problem number 20. We're going to evaluate this line integral through a vector field, okay, where f is vector field, x plus y squared I, so we're going to have an I component, plus xz, so it's going to be three-dimensional, j, put this in parentheses, okay, plus y plus z for the k component, r, our path, parameterizing t cubed I, oh sorry, t squared, get my next one, t squared, I t cubed j, there we go, minus 2t k. And t ranges between 0 and 2. So that's just given to us. It's not explained what that may look like. That curve is provided for us in the problem, okay? And then we have that vector field. I try to put up that link for graphing of vector fields. Hopefully it was supportive with GeoGebra, okay? But again, we're kind of imagining having this field act along this particle traveling along this pathway. Okay, and I think I had done previous work where we had parameterized a curve. If not, I can put another link up there, and you kind of see what pathway this particle is following. Okay, all right. But with that said, pardon me, integrating, that's a dot product. These are both vectors. We're dotting to get a scalar result. Okay. All right. That dr that means we're taking the derivative with respect to t of that r of t vector. Okay, t squared I plus t cubed j minus 2t. Make sure I got my things here. Okay, so that derivative dr dt, okay, is going to be this r prime, right? Taking a derivative component-wise, 2t I plus 3t squared j minus 2k, or that dr r prime times dt So we're going to get, switching to this notation a little bit quicker, cleaner, if you ask me, that r prime times dt, right? So we're going to see, we're going to replace that dr with this vector we're going to be dotting with, all right? So then, taking a second here, again, that's going to be that kind of f of x, y, z, g of x, y, z, h of x, y, z. So we have these functions for f to give us our vector field that we're dotting with that are prime dt, right? So that's going to be that x prime, y prime, z prime of t dt, right? Taking those x, y, z components from R, I know, kind of mixing notations here, dt. So there's that dot product. We'll distribute, add through, okay? All right. So with that in mind, let's check out what that vector field f looks like, right? It was x plus y squared I plus xzj plus y plus z k r of t was t squared, t cubed, jumping to this notation, negative 2t for the k. So exactly, this is our x, y, and z. So that means our vector field f, x, which was t squared, plus y squared, y was t cubed. The j, x times z, x was t squared, z was negative 2t. Then finally the k, the z component here, y plus z, t cubed plus z negative 2t. So f becomes t squared plus t 2 to the third power squared. 3 times 2, we get t sixth. T squared times a negative 2t, negative 2t cubed. T cubed plus a negative, so minus 2t to the first. We had done our dr component up above here. 2t, 3t squared, negative 2 dt. So all that together, we're going to be integrating RT, remember, ranged from 0 to 2. Okay, so limits of integration there. F t squared plus t to the sixth, negative 2t cubed, t cubed minus 2t, dotted 2t, 3t squared, negative 2 dt. So now we have to actually do the dot product. Right? Component by component. 2t cubed plus 2t to the seventh plus negative 6t to the fifth power plus negative 2t cubed, negative 2 times negative 2, positive 4, t to the first, all of that dt. All right, so we're going to get a scalar, all one polynomial result here. So as I start to draw parentheses, combine like terms, rewrite it in descending order, 2t to the 7th minus 6t to the 5th, 2t cubed minus 2t cubed, those go away, plus 4t, that's dt. And that one again, polynomial, power rule, away we go to evaluate. But setting those components up, a little tedious, of course, but now we're integrating across that path through that vector field, right? Kind of thinking of what forces are pushing along that particle as it tries to make its way through that vector field, okay? All right, so hopefully those are some decent examples to get us started in evaluating these line integrals from our text, okay? All right, stop sharing there. Questions, concerns, please let me know.